Good morning, everybody. We're going to kick things off with number 3 here. This is a common style question on the AP test in the multiple choice section, although you haven't seen one like this before, but I think it's going to make sense as soon as I explain it. So, rho of x is it's a density function. Pay attention to the units. It's in trees per square mile, and it describes how dense the trees are from the beginning of the forest moving backwards toward the other side of the 5 mile side of this whatever patch of trees. So I guess maybe they're not that dense, and then as we get closer to the 5 mile side, trees are getting more and more dense. Who knows what rho is? It's just know that it describes the density of the trees. So we're trying to figure out how many actual trees we have, and so we would want to integrate trees per square mile in order to get back to just normal trees. So I want to integrate my rho of x function. That means these are out. You want to integrate rho of x. You want to integrate trees per square mile to get back to just trees. You don't want to integrate rho prime. Rho prime would be trees per square mile, and that's not the function we want to deal with. So it's one of these two. We're going to integrate trees per square mile to get back to trees, and we should do it from, well, obviously from 0 to 3. That's our only option. We're going to integrate from 0 to 3, and I think it should make sense that you're going to be multiplying by 5. You're multiplying by 5 because the units are trees per square mile, so when we integrate, we're just going to get the trees in that square mile patch. So I want to multiply it by 5 so that I can get all the trees in these 5 1 square mile patches. Hope that makes sense. Okay, for number 4, we're given a function e to the sine of x, and we want to know how many times f prime has a 0. So how many times f prime, equals 0 on the interval from 0 to 2 pi. So that should be easy enough. Let's just find f prime. The derivative of an exponential function is itself times the derivative of the exponential part. So there's your derivative, set it equal to 0, and solve. Well, e to the sine of x, that's never going to equal 0. This is 2.7 and change. No matter what I raise it to, it's never going to be 0. And we've got cosine, and that equals 0. Pi over 2 and 3 pi over 2. So there you go, 2. In number 5, we're going all the way back to the beginning of the year with limits. If we attempt to just plug 0 in, we're going to get 0 minus 0 over 0, so we get 0 over 0, which is great. That's one of our indeterminate forms, which means we get to use L'Hopital's rule. So instead of evaluating this limit, we're going to evaluate a different limit. We're just going to take the derivative of the top and of the bottom. And then we're going to try direct substitution again. Now if you plug in 0, we're going to get 0 minus 1 over 0 plus 1, so we get -1. Cool. If you got 0 over 0 again, you would just apply L'Hopital's rule again until you finally get a real number. That's it. D. Okay, for number 7 here, you need to use the chain rule and some trig. So let's just jump in and use the chain rule first. We'll find f prime. This stuff is all right now raised to the 1/2 power, so bring the 1/2 down. Now all of that stuff is raised to the -1/2, and then you take the derivative of the inside portion. And let me just take a second to rewrite this. 1/2 of 4 is -2, and move that stuff to the bottom just to clean it up. Okay, that's f prime. What I want is f prime of pi, so we're just plugging pi in. cosine of pi is -1. The sine of pi is 0. So we're going to get 2 over root 2. I don't see my answer here, so I guess I have to rationalize. And that's better. Root 2 is my answer. Okay, here in number 12, we're going to take the integral of this ugly looking thing. And you may be tempted to pick b here because you might think you're allowed to just give this denominator a negative exponent and then pop it up by 1 and then divide by it. It seems tempting and that would give you that answer, but this doesn't work because du would be -2x. And if you really complete the whole u substitution going that route, you'd see it's not going to work out. So you need a different technique. The answers should give you a hint. You're probably going to try to make it fit the arc sine mold. So if it's going to fit the arc sine mold, then u would be the square root of this term, and that means du would be just dx, and a would be the square root of this term, so that's 2. And as long as you remember the arc sine formula, you go right to the answer. It's just arc sine of u over a, and you're done. Okay, I got a few requests for number 16, and there's no surprise there because this is a weird question. It takes a few minutes usually to remember what the trick is behind this question. You're given a function, but you want its inverse and then its inverse's derivative, and then you want to plug in 0. So we're given f, we're given this weird factoid for some reason. I'm going to come back to that in a minute. You are told that g is the inverse of f, and you want to take the derivative of that function, then plug in 0. So let's just clean all that up. We want f inverse prime of 0. So technically, if I go the long way around, I want to take the inverse of this, and then I want to take the derivative of that, and then I want to plug in 0. And that's not a bad game plan if that's possible, but it isn't here. You can't always take the inverse of a function, and this is an example of when you can't. You can try it by hand yourself, but you're not going to be able to do it. So instead of plugging 0 into this function that I can't find, I need to figure out something that I can plug into f prime instead. I'm not plugging 0 into this. This is a totally different function, but this guy's derivatives and this guy's derivatives, they're related in some way. We'll come back to that at the end. So the trick is to figure out what you're going to plug into this, and that's where this factoid comes in handy. Now, they didn't have to just give us that. If they hadn't given us that, then since I want to plug 0 into this function, I want to set the original function equal to 0 and solve. Although if you try to solve that by hand, you can't really do it. You can probably do it in your head easily enough, but they took out all the guesswork for us. That's what this is here for. I'm told that if I plug in -1, I'll get 0. So I don't have to do anything by hand. I know that plugging in -1 will get me 0, so the solution to this is -1. So instead of plugging 0 into this function, I'm going to plug -1 into this function. And we get -3. Now you got to remember how the derivatives are related between these two functions. They're reciprocals of one another. So if the slope of this function at this point is -3, then the slope of this function at this point is -1/3. Okay, I got a few requests for number 17, but it is pretty straightforward. I want the slope of the tangent line to this function at this point, which just means get the derivative, plug in 1, and then you're done. So let's take f prime. Make sure you're using the quotient rule properly. We got the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And then you can clean that up now if you want, or just go ahead and fast forward toward the end and plug in 1. 1 plus e times e minus e times e. And so I think if I distribute that e and put these together, there we go, they'll go away. And it looks like we're left with e over 1 plus e squared. There you go, B. All right, for number 19 here, you're being tested on your knowledge of the second fundamental theorem of calculus. You're taking the derivative of an integral function. They also did mention something like x is greater than 2 at the beginning of the problem, which you can kind of just ignore. It's just there for clerical reasons. If x was less than 2, then think about what your bounds would look like. You'd be going from 4 to something less than 4. So you'd be integrating backwards, and then things would get a little wonky. So they're just saying x is definitely greater than 2, meaning you're going from 4 to something that's definitely bigger than 4. So you can use the second fundamental theorem the way you think you should. So to take the derivative of an integral function, you just replace your dummy variable with the entire upper bound. So we have 1 minus the square root of x squared, so let's just say x, and then multiply that whole thing by the derivative of the upper bound, which is 2x. And that's A. Okay, here we are at number 20, and we have a slope field and 4 possible differential equations, one of which is modeled by this slope field. So you'll see I just copied 4 of our points from the slope field, and I'm going to try to see which one of these makes sense with all 4 of these points. That's the trick with these kinds of questions. You really don't have to look at the whole thing. You definitely don't have to solve anything. You just need to figure out which ones don't make sense. If you can find one point that doesn't make sense with that differential equation, you can get rid of it. For example, x minus y. If x minus y is your differential equation, then this point doesn't make any sense because the point 3, 3 should be giving us a slope of 0. And on the slope field, it looks like the slope should be negative 1-ish. It's definitely not 0, so for that reason, we can get rid of that. Now, let's see. I think this one, no, that one does make sense. At 3, 3, the slope would be negative 1, so I can't really get rid of that one yet. Let's slide over to here and let's take a look. Negative 3, 3. So if this one is correct, then negative 3, 3 should be giving me negative 3 over 3, so I should be getting positive 1, which I'm not. Clearly on the slope field, I'm getting something negative, so this one's gone. If 1 plus y squared is my differential equation, I'm going to go back to this one, then at the point 3, 3, my slope should be like 10. That's definitely not right. But this one makes sense. 1 minus 9, okay, so negative 8, I'd buy that. I don't know that it's definitely negative 1. I just copied this by eyeball. It might be a lot steeper than that. Let's see, at negative 3, 3, same thing, right? Because it only depends on the y value. So it would also be negative 8. Here at 3, negative 3, then I would be at 1 minus negative 3, so 4, definitely something positive. Same thing would happen here. So I found a reason to get rid of all these. I haven't found a reason to get rid of that one, so that one must work. D. Okay, 22 is kind of tricky if you don't remember the alternative definition of the derivative. This is the one we spent some time on. This one might look a little bit more familiar, but this is an alternate version of that. So all of this just means you're taking the derivative of f at a. So this is going to produce, just this part, the limit part, is going to produce the slope at a on the function f. Just like this would do. This thing gives you the derivative of f. This thing gives you the numerical slope of f when x is a. So if this whole thing equals 0, that's just saying that f prime of a equals 0. B. Okay, 23 looks way more intimidating than it actually is. You'll need to integrate this nasty thing from 2 to 8 using all these fun facts given to you in the table here. If you recognize this, I hope you do, it's just the quotient rule. So you are integrating this quotient rule, which should back up to g over f. And we'll evaluate that from 2 to 8. Let me just explain that again. If I take the derivative of g over f, then I'll get f g prime minus g f prime all over f squared, right? So if you integrate all of that junk, you get right back to just g over f. Just pay attention to the order of things. Don't assume it would be f over g just because that's how we see the formal definition of the quotient rule. Pay attention to what's on the bottom here. So if g over f is the original function, I just need to evaluate it at 8 and at 2. So that's where the chart comes in. I'll get g of 8, which is negative 6, over f of 8, which is 3. And then g of 2, which is 2, over f of 2, which is 1. So negative 2 minus 2, or negative 4. Okay, number 24 has a lot going on here, a lot to read, so I actually worked out a bunch of stuff first so I can just explain it. G is defined as an accumulation function from 1 to whatever x is. T is a dummy variable, and here's a function of f. So G is going to be calculated by integrating on the f function, starting at 1 and going either forward or backward to whatever x is. So I went ahead and just found the areas of these little triangles just to make the integration easy, because we're going to wind up doing the same calculations over and over again. This little triangle down here has an area of 1.5. This area is 2, and if I draw a straight line down from where this segment ends, that triangle should also have an area of 2. Now notice I also didn't call that one negative 1.5. I just want the area at 1.5 because it's only going to be negative 1.5 if I'm integrating forward. Remember, if I'm integrating backward, everything's opposite. So I am just going to play it by ear. If I'm integrating backwards, then these things are going to be negative and that's positive. And if I'm integrating forward, then these are positive and this one's going to be negative. So g of negative 4 means I'm going to integrate from 1 backwards to negative 4. So starting here, go backwards to negative 4. So that means that'll be positive 1.5 minus 2. So that's negative 1.5. G of 1, well, that's just 0. Integrating from 1 to 1 gives me 0. Done. G of negative 2 is also going backwards from 1 to negative 2. That'll be positive 1.5 because I'm going backwards. It's below the x-axis, but I'm going backwards, so it's positive 1.5. And G of 5 is the area if I integrate from 1 over to 5. So I am moving forward, so this area is going to be positive, and that's 2. And these are the 4 values that I'm trying to arrange, and it's definitely going to go in this order. G of negative 4, then G of 1, G of negative 2, and then G of 5. So that is A. Okay, in 25, we're given a related rate. The circumference of a circle is increasing at the rate of 1/2 something for somethings. We want to know at what rate the area is changing when the radius is 4. So I need some relationship between A and C because I know something about C. I want to know something about A, so I need some relationship between A and C. And there's not a direct one. You do have a relationship between the radius and the area, and a relationship between the radius and the circumference. So obviously we could come up with a formula that relates area and circumference, but we might as well just jump from circumference to radius and then from radius to area. So let's start with circumference is 2 pi r. That means dc dt is 2 pi dr dt. I know we haven't done this in a while. You're just going to take the derivative of everything with respect to time. So all derivative rules as normal, just tack on a d something dt anytime you're not taking the derivative of an actual time variable, which obviously we're not here. So dc dt is 2 pi dr dt, and here we know this. So dr dt is 1 over 4 pi, regardless of what r is. So that was easy. Now we're going to pop over to area. Area is pi r squared, which means dA dt is 2 pi r dr dt. And this is what we're trying to solve for, so let's just plug everything in. 2 pi, my radius is 4, and dr dt we figured out from the first half of the problem is 1 over 4 pi. So this is nice, the pi's cancel, the 4's cancel, and I'm left with 2. So the area is changing at 2 somethings per whatever. Okay, got a few requests for number 26, and I'm pretty sure it's the piecewise function that scared you off. So f is defined as just 2 lines. We've got y equals x up until x is 0, and then after x is 0, it's going to be the line x plus 1. But you're not integrating that, you're integrating x times f of x. But we still need to be concerned with like this jump over point here. That giant jump in the graph is going to happen at the same place on this function for the same reason. We have a giant jump in this graph, so obviously this graph is also going to have a giant jump in the graph. So let's split this up into the integral from -2 to 0 of x times this function, so that's just x squared, plus the integral from 0 to 1, and we're going to do x times this function, so x squared plus x. And then just integrate everything. 1/3 x cubed from -2 to 0. This will be 0 minus -8/3. Sorry, this is getting kind of small. Or just 8/3. Plug in 1, we'll get 1/3 plus a half, minus 0. So I'm getting 7/2. Done. Now, only one of you asked for help on 27, which means I know most of you either used your calculator or you skipped this one, because this one gets wonky in the end here. It's straightforward in the beginning though. We want to find the average value of this function over this interval. So remember how I think of this. We have the area of a rectangle that is equal to the area under the curve over the same interval. So if the rectangle is 4 units wide and f of c units high, f of c being the average value that we're solving for in the end, let's set that equal to this integral. Okay, now be careful with this. Technically we need u substitution, where u is 1/2 of x and du is going to be 1/2. So I need to fudge and fix so that I have my 1/2 dx in here. Now you can do the formal translation if you want to, or you can just recognize that this goes to 2 because of the fix times the sine of 1/2 x. Be careful if you do the formal u substitution to actually change everything. Change the integral and also change the bounds. Now if I plug in 0, I'm going to get 2 times the sine of 0 minus 2 times the sine of -2. The sine of 0 is 0, so I just have -2 the sine of -2. Don't forget the goal is to solve for f of c in the end, so divide by 4, and that's how we get -1/2. the sine of -2. And this is how I know most of you didn't do it, because I don't know how many of you remember these rules from pre-calculus. The problem here is this answer is not here. So hopefully you just either guessed A or D. But here's the trick. Whatever, if you picture two angles, like -2 and 2, clearly we want our angle to be 2 and not -2, since that's the only choice. Well, here's -2 radians and here's 2 radians. How are the sines of those angles related? They're just complete opposites. This has a positive sign and this has the exact same negative sign. So this is not factoring out a negative. Please don't think that that's what I'm doing. But the sine of -2 and the sine of +2 are just completely opposite one another. So I can call this +1/2 the sine of +2. But please don't think that that's factoring out a negative. We're utilizing a property of the sine function. So that gets us what? D? Done. Okay, 28 is a weird version of U substitution. It gets a little funky, and I'll show you where. But hopefully you at least whittled this down to 2 possible answers. If I'm doing U substitution, my bounds are going to have to change. Please don't forget to change your bounds. So I'm almost positive they are not still going to be 2 to 8. If U equals this, then my old X being 2 means my new U is going to be, well, still 2. All right, so that one doesn't change. But when X is 8, then U is going to be 4. So my new bounds have to be 2 to 4. So it's definitely one of those, and I hope you got rid of B and C. Now let's try to figure out what the rest of the U substitution is going to do. If this is U, then du is 1/2 all this stuff to the -1/2 times 2 dx. Don't forget your chain rule there. If I just clean that up, I have dx over root 2x. And this is where it gets a little weird. Like, I don't have an extra root 2x in here to get my du to work. But root 2x is u. So it actually kind of translates really nicely. Dx over u, or if I rearrange this, dx is, if I multiply both sides by u, dx is u du. So I know my bounds changed to 2 to 4. Dx turns right into u times du, and on the bottom I have u plus 1. So that gives me D. Okay, for 29 here, we're trying to find the volume of a solid of revolution. We've got the area trapped between x minus 3 squared, which you are supposed to be doing this without a calculator, so hopefully you know this is just a normal parabola slid over to the right 3 units. I know it's going to intersect here. Its y-intercept is going to be 9, and my other boundary is y equals 9, so that's nice. It's just going to be this area right here. That's going to get revolved around the top of itself, y equals 9, which is nice. So we only need 1 radius. This is not going to make a washer. All of these sample rectangles are going to make full-on discs, no holes in the center, so you just need 1 radius. So it looks like we're going to integrate from 0 over to 6. And we just need pi r squared. The radius is going to be 9 minus the function. Squared. And we're good. Let me see, 29, we need, looks like B. Nope, I lied. Looks like Looks like none of these. Okay, it looks like none of these because it's going to be B or C. Instead of integrating from 0 over to 3, from 0 over to 6, let's just go from 0 to 3 and then double it. So that's why you see some answers with 2 pi. So let's just go from 0 to 3 of the exact same thing. And now, 2 pi, now we have B. There you go. Okay, for our last question here, we're given 2 integrals over the same function. If I integrate f from 0 to 1, I get 5. If I go from 0 to 7, I get 1. I'm also told the function is even. Remember that means you have y-axis symmetry. So whatever's happening on the left of the y-axis is a reflection of whatever's happening on the right side of the the y-axis, which allows me to evaluate this from -7 to 1. Even though I don't know anything, I seemingly don't know anything about what's going on between -7 and 1. This area, whatever the function is doing, that area is going to be exactly the same as this area. This part of the curve is a reflection of this part of the curve, so they should have the same integral. Now the integral from 1 to 7 can be broken up into the integral from 0 to 7 minus the integral from 0 to 1. I go from 0 all the way to 7, and then I just take out the bit that was from 0 to 1. So this is 1, this part is 5, and then we go -4b. Got it. The last thing I'm going to leave you with today, guys, is a quick update on the AP test. We just got word a couple days ago from College Board that they're making some changes to the test so that you can still take it, but you'll take it at home. Big change is that there's not supposed to be any multiple choice. And they're telling us that it's going to be a 45-minute test that will be only free response. And like I said, you'll take it at home on a computer, I assume. Before you get too excited about that, you should know that College Board has issued at-home tests before, and I don't know how they do it, but they make sure cheating is impossible. So you don't count on being able to Google any of the answers or somehow being able to ask a friend for help or getting them to take the test for you. I don't know how they do it, but I know that they make these tests cheat-proof. Anyway, on our end, we're just going to continue practicing the way we always have. I know there won't be any multiple choice questions on the test, but multiple choice questions are a great way to nail down all of our basic skills. So we're going to keep doing multiple choice practice as well as throwing in some free response practice. Anyway, that's all I have for you today. Just look over this video. If you have any follow-up questions, then shoot them my way and I'll get back to you. You probably know what tomorrow's assignment is going to be, so you can get a jump start if you want to do that. Other than that, you guys have a great day. I'll talk to you tomorrow.